real side of tech and operations. I've got an awesome guest today, Clint, and we will be talking a little bit about plunger lifts. And I think the biggest thing to start with is the why behind the conversation Clint and I are having today, which is plunger lift is everywhere in U.S. onshore oil and gas. It's a headache. It's a challenge, and it doesn't have to be so with some of the insights that Clint's going to share with us today. So I want to welcome Clint. And before we start diving into the topic here, Clint, why don't you tell us a little bit about yourself and Kaizen Well Solutions, and let's just hear about your background a little bit.
Yeah, well, thanks, Spencer. I've been working in the oil and gas industry since mid 80s. Started out in operations and construction, and found myself drawn to well optimization, and ended up working with several different companies early on, Stroll Tools and a bunch of other ones that are probably not around anymore. But kind of fell in love with plunger lift and gas lift and all that type of optimization, and just drew me in. So for the past, I guess, 30 plus years, that's basically what I know. It's basically what I've been doing. And, I've built a couple of companies over the years. The latest is Kaizen. We're based out of Canada for the most part, but we do have a US division as well, which is AppSmith division. And we really basically focus on gas lift and plunger lift. Those are our two main things: design and equipment, and troubleshooting and different things like that. So,
they're two really good things to be focused on, because if you look at what's growing in the U.S. onshore oil and gas space, it's plunger lift and gas lift, either combined or separate or in different phases. So those are two really, really good areas to be focused on. So nice.
Yeah. I've really seen the application of gas lift increase quite a bit, especially in Canada. Up until a few years ago, there was very little gas lift onshore. So it's been an interesting learning experience as well, to when we start combining the GAPL and all that, and how to make things operate. So it's been quite a learning curve, I think, for everybody involved in the industry.
Yeah, no, learning curve is a good way to put that, because it's been hard, speaking from my own experience. So that's awesome. And your background is long lasting. And, I think when we were talking here in Denver, what struck me was your experience in the field. You've touched wells. You're not just someone who knows plunger lift from afar. Like, you've tracked them. You have been a part of design. So tell us, if we're talking plunger lift today, why should we listen to you? Because your experience is huge. So tell us a little about the details of what you've done. It's deep, right?
Yeah. Well, why people should listen to me? Well, really what people should be doing is listening to everybody and gathering data, not just me, obviously. But especially when we're talking about shale, it's been such an amazing learning curve. And myself, with all the years I've had, I learn stuff every day. And so we should all be listening to each other, and conversations like we're having today and sharing is key to improving and moving things forward. But I think from my experience is that I've always approached it from the field. I've always I froze my ear on the side of a lubricator. Anybody that's in northern US or can't understand what that is, well, you're listening for that plunger to come up. I've installed them. I ran wireline trucks. I've done basically everything around it. So and the other thing I feel that I guess maybe because I'm so passionate, I want to understand why it does something. So if I don't know, I will spend the time and effort, and I have great people around me. My team is great, to gather data and try to correlate, like what is repeating, what is happening over and over and over. If a plunger is doing something or a gas lift is doing something, what are the patterns? And that's one of the things I've really found with shale and horizontal is pattern recognition is much more important than, say, rules of thumb. And but that's a whole long conversation on its own. but yeah, it's an interesting change compared to vertical wells, where is really rules of thumb worked well, and you had a certain amount of rise time and a certain amount of fall time, and it's kind of in a nice neat box. And when we talk about horizontal wells, a lot of that stuff gets thrown out. And again, coming back to the learning, it's really understanding the patterns. What's your gas flow doing? What's your plunger doing? What's your casing doing? And I've watched through multiple different areas, Eagle Ford and Permian and the Montney and the Duvernay up in Canada. And, the patterns that you can see are kind of move through all of these horizontal wells, different depths, different pressures, but there's certain patterns, and it helps you recognize them. And that's one of the things that maybe is really hard to understand, or not understand, but to learn is to kind of put away some of the learning that we had on horizontal wells, on vertical wells, and use the patterns, the understanding why that stuff is different now in a horizontal well, for example. But,
yeah, that's something that, it may be your first time hearing this, like, news flash to everyone, but you can't treat a horizontal well like you can a vertical well. And that's like, we've been drilling horizontals for a while, but I think we're just now realizing that this, not just now, maybe in the recent years, kind of figuring out that, gosh, I can't treat the way my rules of thumb I was on vertical wells, carry them forward to my horizontal wells, inspect everything to be rosy. So that's a really interesting piece to bring up there. And yeah, that's a challenge I think we're all facing right now, which is why I think plunger lift is a critical thing to be talking about in the industry.
Yeah, for sure. Yeah, but it's definitely a thing that we can all learn more about. I mean, the learning never stops. I can guarantee it. So
yeah, and it's best to learn on the job, and that's where you've had your experience. So we appreciate where you've been coming from on this. So that is awesome. And I think some of the topics we discussed would be interesting to our listeners are really just like the problems that we face day to day, and thinking about practical ways that we can get better at solving them. So what I think is most pressing from the customers that we work with at Task, and I'm sure you have at Kaizen, is a plunger selection. Like, when do I swap from a ball and sleeve to a padded or a Venturi or whatever type of plunger? It's the plunger selection, which I think is really challenging for just anybody to figure out and to get it right. And is there a right? So I think that's one thing I really want to hit with you today. And then also the maintenance element to it. So everyone has to do inspections. Everyone has to swap out plungers. And they swap with the same type, they swap with a different type, but maintenance and type, I feel, are two pressing problems that I think we could shed some light on here today, Clint.
Yeah. Well, I guess when we talk about type, I mean, what do we mean by type? And there's, I'm going to break it down in kind of how I think about it, so everybody understands what I'm talking about. But there's kind of, to me, three types of plunger, and there's the ball and sleeve, or a two-piece type plunger. There's a free cycle, which can encompass several different styles, where you have a rodded surface and it trips a valve open. You could have a rod built into it. It could be just a ported type, like the Venturi type plunger. So I would kind of classify that as a free cycle. The Venturi really isn't a drop against flow plunger, but it falls faster than, say, a conventional plunger, which would be, no bypass port, no valves, no anything like that. So so those are the three types of plungers, and I kind of break them up into those three groups. And I do that because there's a real distinct difference in the way I look at a conventional solid or a non-bypass plunger versus a free cycle or a two-piece. And when I'm this kind of the line in the sand, and there's a little, I guess it's not a line, but the road in the sand, it's a little wider than a line, is that when I'm looking at a conventional plunger, it's really about your gas to liquid ratios, right? And how much, what is your total production, gas volume and liquid production that you're going to make? So I use a lot of the rule of thumb, the 400 to 1200 standard cubic feet per barrel per 1,000 feet deep is kind of a, if you fall in that could be a conventional type plunger. When I'm talking about free cycles and two-piece, I consider them a velocity plunger. And they're not really looking at building up pressure typically. Mm-hmm. What I use is I'll say, well, if I can get my wellhead velocity, if I believe I can get the wellhead velocity to 50% of wellhead critical to probably 60% of wellhead critical, and as your well gets deeper, that percentage has to climb up a little bit, but somewhere in there, it's probably a good candidate for free cycle or a two-piece type plunger. And the reason for that is especially in the two-piece or the pacemaker style plunger, you really want no off time, which is critical in that plunger. If you have any sort of off time that allows that plunger to get to bottom without flow, your chances of damaging plungers and bottom hole springs is extremely high. Even with lots of fluid, those things can move so fast.
Even more on that, Clint, on the two-piece, you mentioned like you shouldn't have any off time. Like what happens from what I've seen is people have 5 or 10 minutes. They'll start running it like the thing they should be running next, which is your free cycle, right? So right. There's other consequences on the ball and sleeve, right? Around, you mentioned to me before, the weight of the ball, and actually it's a poorer seal because it's shorter, right? And the ball can kind of pop out. So tell us about the consequences of saying running this different type, being the ball and sleeve, in an inappropriate application.
Yeah. So a ball and sleeve plunger, for example, it is typically inefficient because they'll usually have a little more, less OD many times. They have a very thin wall, so they don't have a lot of ridges to create that turbulence. They're typically a solid. You can get some pads in that, but I would always stay away from that. There's too many moving parts in a very high velocity plunger. But it gets away with that because you can make so many cycles.
Sure.
So who cares if the plunger only lifts 40% of the liquid it starts with? You can make 150 cycles a day. You don't really need to shut the well in, so you can actually make up that inefficiency. Mm-hmm. But as you start shutting the well in, efficiency becomes a lot more important because you're starting to lose your total production time, right? So if I got to shut that well in with an inefficient plunger for 5 or 6 minutes, but I got to do that 25 or 30 times a day, I'm losing a lot of production time.
Sure.
Where if I use even a free cycle that might be a longer, a two-piece, a solid but a longer seal surface, or a padded style, or I have a better seal efficiency, I can lift that fluid instead of needing 20 or 30 cycles, let's say, to lift that amount of fluid out of the well with 5 minutes of off time. I can maybe do that with 15 minutes or 15 cycles or 10 cycles because it's losing less fluid as it comes up. So it can make a big difference, and that's when the efficiency starts to make a bigger difference. I mean, two-piece plungers are really, I always look at them as the dragster. I mean, they're the top fuel. You got a well that's screaming and you want to run that thing up in there, and you're running down and grabbing a little bit of fluid and zipping it back out and maximizing your maximum flow. But with the dragster, your maintenance and your cost to run it is much higher. So your payback has to be much better. Yeah. And the second you start shutting it in, and people don't maybe realize this, but a two-piece plunger, in many examples, they can fall, between 5,000 and 6,000 feet a minute easily, even in a well that's flowing. And if you have a well that, if you're shutting a well in for 5 minutes, guaranteed it's at the bottom, right?
Yeah.
And if that thing is traveling and there is, it can get back to that speed very fast. So if you have a bunch of liquid strung out through the well, it might slow down that plunger as it's going through the liquid. But is there liquid at the spring? Or, because again, you're not shutting in very long. So that liquid is probably, that's in the tubing, could be strung out. It's not sitting there or may not be sitting there as a big, column right at the spring. So if it gets through that liquid and then hammers the top of that spring, you have a tremendous amount of force. Your kinetic energy in those is incredible. So,
and regardless to, the arguments out there, I've heard of, well, look, I'm not having ball damage. Like my ball isn't dimpled. My I can still keep running this ball and sleeve. It's the question at the beginning was around like it's just inefficient to be running something that only seals, for or prevents water leakage by 40%. So
Yeah.
it is it may not be damaged, but it is damn sure inefficient, which is becoming the argument you brought up is like if you're having shut-in time, you probably need to start transitioning to what you were mentioning on the free cycle piece. So how do people know like when? Because I feel like that's one of the bigger questions of with the operators that we've worked with is hey, look, I put my free cycle or I put my ball and sleeve plunger in here. It could work really good for months. And then you start having some production issues and liquid loading. And so you increase the off time, but you don't change the plunger out, right? So you just can't kind of keep working your way to this volatile, unreliable well. And then they start questioning, is it the plunger or should I change it? So how do we get better at knowing when the right time to transition on these newer wells is?
So when a two-piece plunger, and I would call this a hard and fast rule that everybody should follow. If you have to shut that well in for any longer than it takes that plunger to come out of the wellhead, right? So you shut it in, takes you a few seconds for the valve to close. And then once it's closed, the plunger slid out of the wellhead, come off the rod that's inside the lubricator. If you need to shut it in for any time, you either to build up enough pressure to get it to come back up or to get it to fall far enough because there's a really high rate, you need to do something. First of all, the second you're shutting it in more than that takes for it to come off the rod, in my opinion, you need to look at changing plungers. Okay. So that's kind of a hard and fast rule. Now, it doesn't mean, so if I got a really high rate, does it mean I can't use that plunger? It doesn't mean that. What it means is I may have to change sleeve weight, I may have to change ball weight, something like that. And that's a whole other conversation about how that's all supposed to work. And that's kind of been a lost art as well. I mean, the way your ball combinations, but what I see happening is because people want to get the efficiency, they start seeing the plunger not cycling, so they start running longer sleeves, even though they're shutting in. Right. So now what happens is they run a very heavy sleeve and they're shutting it in. So yeah, they weren't having trouble before when you run a 6-inch or an 8-inch or whatever. So, but you start putting all that extra weight, and again, your kinetic energy impacting that bottom hole spring is huge.
Now, Clint, you just said something right there that because you're an expert, you know this. But why is a longer plunger better for when things are getting inefficient?
Well, it's the longer the plunger is, the more what we call differential resistance we're causing across the plunger. Now, what really creates a seal around the plunger is the gas that's flowing by it. The gas going by it is what is holding the liquid up. It's not like a swab cup. It doesn't work that way. It's not a positive seal. Like if you ran down the wire line with a plunger on the end and you went scoot out of the well, the chances of lifting any fluid with a shut, just trying to swab like you would normally is practically zero. You may get a little bit, but it's really not pulling anything. So what creates the seal around the plunger is the gas that's going by, and it's differential. So there's you got to have a certain pressure drop across it, right? So and the pressure drop is required to make that plunger move, you got to have a differential. The plunger, whatever, is 3 psi or whatever the number might be. But as that plunger wears, or if it's shorter, you just don't get the same pressure drop across it. So you have to move more gas across it. I don't know if it's a right analogy, but I always explain to the operator, say, what's your differential across an orifice plate if you're running a 1/2-inch orifice or a 1/4-inch orifice plate, and if you're running a 1-inch orifice plate? I mean, you got to run a lot more gas to get the same differential. Well, whether your plunger is wearing out and allowing more area between the tubing wall and the plunger, or the plunger is shorter or longer, it impacts that. So it's all about what differential can I create across that plunger with the gas that's going by it. And as that length gets longer, I create a bigger differential. and it makes those plungers more efficient. Basically, and when we talk about efficiency, there's a lot of ways of getting, what does that mean? But it's really about how can I make that plunger move with the least amount of gas going by it that will push that liquid to surface.
Yeah, that's a really good way to describe that.
So
yeah,
I'm not sure, but yeah, so that's kind of that's why longer plungers. And I mean, there's probably some advantages on it's really important on a solid plunger, right? A solid seal ring type plunger, because the what you make up for the inefficiencies on the OD, because it can't expand and stay close to the wall, and it has to at least be drift, or should be drift, so it can go through the collars. You got a lot of bypass area, so you have to make that up with length. And we did some testing on some different plunger lengths, and we found that a 24-inch 2 3/8 solid plunger almost performed exactly the same as a dual pad, a good quality dual pad plunger, as far as lifting ability, and the amount of gas it required to move it, and all the matrix that we use to check that out.
And that's really interesting you say that, because people think the only way to seal is using a padded plunger. And, that right there, using length to compensate when situations you can't use a pad, you can still be efficient, right? I think that's a really interesting point you just made right there. And I hope the audience is listening to that, because you don't have to, have the pad if you are in a situation where you can't afford it. Maybe it's paraffin or something, and length can assist in some of the better sealing, right? So that's a really good point there. And, I'm glad you shed some insight on your experience with the length stuff, but you did glaze over one thing you did in the past. Didn't you tell me one time you were part of like the first people to help design the ball and sleeve, right? Weren't you involved in that?
Yeah, I worked with Mike Wells and Mark Wells at MGM I had my company up in Canada, and I got introduced actually through a working relationship to Mike, and just tell me about this great plunger that he'd been using down in the States. So I went and talked to Mike, and brilliant guy, really good guy, and still talk to him today. But he had this 2-piece plunger, this pacemaker, and I got to learn about it, and I thought, man, this is just a brilliant idea. But there was a lot of learning that had to go around this, because again, it's like giving a guy with a learner's license, again, a top fuel dragster. We had to understand how the thing performed. But through time, when you understood that plunger and how it interacted with the well, you could do some amazing things, like wells that we could never produce with plungers before. High volumes, like high liquid, like we were moving, and these are vertical wells back then. There was very few horizontal when we started, but you can move 150, 200 barrels a day with a plunger, which was completely outside of the box on a real strong well. So yeah, and also learning, weight. What's a weight ratio between sleeve and ball? Now you got to also remember there's kind of two-piece plungers out there. There's the one that uses the ring, which locks the ball in place. And they're not really concerned about weight, because it's basically locking it in place. And then there's what the pacemaker is, where it doesn't have a ring. And that one, it's the ratio between the plunger and the ball are very important, because if that sleeve and ball are moving up and it ever stalls, or for whatever reason, if the ball is actually the wrong weight compared to the sleeve, it'll fall faster than the sleeve. So it'll be coming part way up, and they separate, because there's nothing locking them in except for the differential across the plunger. And once they separate, that ball goes faster than the sleeve, so it's got to run all the way to the bottom again before it makes that contact, and then it starts back up. So that was one of the big mistakes. I see guys will throw in a real heavy ball with a plunger, and then they have a lot of trouble where it's inconsistent, and that's what's happening. It's separating and can't keep up. So that's really key to understand that. And then when you get into the ones with the locking rings, and they work for a while, but they're mechanical, and we find that the locking rings don't last as long as you would hope. So then you end up having kind of the same problem where the ball is not staying in the sleeve. And if you're running a tungsten carbide ball to get that down to bottom because your flow rate or the amount of fluid, you start all of a sudden getting really inconsistent runs. So even on those, it's good to have some sort of an idea on your weight ratio. You don't want to be way out of whack, I guess, between your weight ratios. And if you want to keep that thing performing for a longer period of time. So.
Okay. So ball and sleeve, pacemakers, we're moving on to, we've just transitioned over to your free cycle. I love the rule of thumb you put out there, which I think is really good for the audience to hear again, which was if you're requiring some sort of off time, if you're doing any sort of pressure build with a ball and sleeve, if you're shutting in any longer than it takes for the plunger to fall out of the lubricator, it's time to switch. So,
well, or it's time to consider again. I mean,
it's time to consider,
right?
Yeah.
If you're shutting it in to build up pressure, it's time to switch. If you're shutting it in because you can't get it to fall, it's time to consider whether you need to be a heavier plunger ball combination.
Okay.
Or
good.
Yeah. So
good clarification. Yeah. And then, so now we've transitioned over and we're looking at free cycle, right? So we've just realized, wow, we're shutting this thing in for pressure build. Because I've seen that with some customers of ours is sometimes you'll see 7, 10, 15 minutes off time with a ball and sleeve, and just trying to transition them to the next phase and getting that buy-in to move towards a free cycle. So, all right, let's go to free cycle. But how do I know which one? There's so many options out there. There's a 5-port, there's Venturi, there's name your combination. There's a lot of options to choose out there. How do I choose the first right one, transitioning from a ball and sleeve over to a free cycle?
I would say the one of the very first things that when I'm talking to the field guys, and we this is a big conversation with a lot of the guys, understanding when do I make a choice. It's really if you just take the plot of the well's buildup, right? How fast when you shut the well in, how long does it take to basically curve off and flatten out, right? And if I'm shutting in a well and in 5 minutes it's basically built up and curved off and kind of flattened out. And, you're getting that very slow build. It's doing one or two things, probably squeezing fluid out of the tubing at that point, past your relieving standing valve or whatever. Then you want a free cycle that has a lot of bypass area because you need to get that plunger down there fast, right? So that could be your 5-port or your large bypass area. But if I have a plunger that's taking, say, 20 or 25 minutes to build up, so you're shutting the well in a little longer, can I get a Venturi or a smaller, slower falling plunger down there in that time? So you kind of let the well decide, not so much what, but understanding how it builds up. And if it builds up very fast, you want a much faster moving plunger. And it's kind of the same with even looking at the 2-piece. If you shut it in and that's typically you'll see a well like that, they snap right up. They're ready to go in a couple minutes. It's a no-brainer for a 2-piece, right? Even though you're not shut in, but you know that it's really responding so fast. The other thing is to consider is packers or no packers. So
great point there. That is a lot of people out there. I've got a friend of mine working in the industry who's like, it's so hard to operate a plunger lift well when I can't see the casing. And again, does that, if we talk rule of thumb for vertical, it's very important to have some casing pressure there because of the buildup. But does it really apply to horizontal? And I know you'll get into that, but packer, no packer, go into that. Yeah.
So again, just staying with vertical wells, if you have a packer in the well, it's much harder to run. Obviously, a conventional plunger. For what you're saying, you just don't have that storage area. So, but if you have a good inflow, you're better than that 50 to 60% wellhead critical rate, or you can get there. It actually works better than a conventional running a 2-piece or a free cycle because you're just everything that comes in is being pushed up the tubing. And you're just getting down there and getting those small bites of fluid and keeping it moving. So and again, it kind of moves into a free cycle plunger or a 2-piece plunger, it's going to be better than 65% of wellhead critical. So your GLRs are probably quite high because, there's a rule of thumb of about 1,200 standard cubic feet per barrel are greater when you have a packer. Well, probably if you calculate it back and forth, you'll find that you're at least that or a little better. And that's when you would run a 2-piece anyways. But if you're below that and you're needing to shut in, it can be very, very difficult to get enough gas to drive a conventional plunger up there because there's just no area to store it.
Right.
Vertical, that's a vertical. In a horizontal, you got to remember, we run tons, well, not tons, but say we don't see a big impact, negative impact with Packers with plunger. In fact, we actually see a positive impact most of the time with a Packer in a horizontal well.
Really? Okay.
Yeah. What we find is, and there's a whole conversation about how fluid moves and fluid gets past the end of tubing and stuff. But if we run a Packer, and you've got this, mile or 2 miles of storage area, and so when you shut the well in, you still have a lot of volume that you can store energy in with a conventional well.
And you're referring to the horizontal. You got a mile or two of just horizontal buildup.
Yeah. So you've got an area to store that gas. Right?
But before it was the casing, you were building up all that right there to kind of help in getting that plunger surface. Now that it's okay to have a Packer because that pressure build and stored energy to push is really in that horizontal.
Is in the horizontal, so you can get away with it, and or you can have some good results with it. So, so it's not nearly as important. And the nice thing about a Packer and a horizontal well is that any of the fluid that moves to the end of tubing is basically forced into tubing and
right,
going down. Where if you don't have a Packer, a lot of times, or every time we've ever monitored it, we'll see fluid actually gets hung up past the end of the tubing. So a percentage of the slug that moves down the horizontal gets pushed past the end of tubing. The energy that was pushing that slug to the end of to the tubing drives whatever fluid went into the tubing to surface, and then of course that energy is dissipated. And as the pressure comes off around the end of tubing, the fluid that got pushed around the tubing starts to collapse back around and starts to enter the tubing, but there's no energy there to drive it up. So you can have a really interesting dynamic about fluid movement downhole when you don't have a Packer and a horizontal. So we've seen this work where we've just gone in and actually put a Packer and a gas lift system in on a well that won't change into tubing, won't do anything, but we put a Packer and some gas lift. Won't even turn on the gas lift. We just turn on the well. And a well that they couldn't keep flowing will take off and flow for another 6 months or a year.
That reminds me of like a funnel. It's like basically preventing the bypass of the water, and it's kind of stopping the water from going to the casing, and it's being like, no, you got one place to go, and it's the tube.
Yeah,
that's very interesting.
And you're keeping the energy behind it. Basically, it's whatever it pushes there, it's going to carry it up. So I don't know if that's always 100%, but we see that an awful lot. I mean, the one problem we have with Packers and horizontal wells is it's a very small percentage of the overall wells we work on. So I got a lot more, but I do know the ones where we've done that we got several examples where just dropping a Packer and took a well and made it perform. Wow. And where it wasn't before. So yeah. There's a lot of horizontal wells. There are so many different things that it can impact the way the well is producing. And the tubing position is critical. Packer, no Packer. I mean, so many things that you got to look at. If you're having trouble, if I was working on a horizontal well and I was having trouble, the very first thing I would do is say, I need to see the completion report, understand where everything is. Am I landed high? Am I landed, in the vertical or in the down in the toe? Where's the end up position? All these things make a big difference.
I think that's a podcast in itself because the horizontal struggles are just there's a lot of learnings that you've had. I know the industry has had that we could probably share out there. So let's make sure we talk about the horizontals and the upcoming one that we got to get knocked out, recorded, you and I. So man, I think what's really interesting you were mentioning there is just the difference in the perception on Packers. Everyone has a negative perception on Packers, but maybe in application being in horizontals, it's not actually a bad thing. That is kind of industry shifting from just the vibes I've gotten from some of my optimizers I've talked with, where they see a Packer and a plunger well and they're like, I wish they would take it out, right? And that may not be so, which is really cool to hear. So I'm glad you shared that. And then I think what I'd like to hear from you is really, you toss some rules out around selecting the right free cycle, which is really around like how the well is building. Well, the question was, what free cycle plunger should I select? And you're like, it's well dependent. I love that because every well's a little snowflake, and they all have their own personalities, and they all have their own Facebook profiles, and they all doing different things. And the type of plunger is selected by how it's building, right? So do you need it to be at bottom in 5 minutes? Like you said, lots of ports. Do you need to be at bottom in 15 minutes? That'd be less, maybe a 1 port or something. So love that synopsis there. I think what I'd like to drive you towards now is kind of just, so we've advanced from ball and sleeve to free cycle, and now we're like headed towards a more of conventional style. And that can be so different duration wise in so many different wells' lives. Like, is that 1 year? Is it 5 years? Is it, is it after 6 months? I think I want to restate the problem we're looking at here is like, when is what we're talking about, like when. So talk to me about conventionals.
Yeah. So a vertical well is easy, right? We talk about the rules of thumb. When you're down below that's when you're down below at 60% or 50% of critical, or wellhead critical rate, you pretty well are moving towards a conventional well or a conventional system. You might get away with like the Venturi or a little faster falling plunger in there as a little stopgap, but basically you're moving towards that needing.
One clarifying point here, Clint, just for the audience, the 50% of wellhead critical. Tell me a little bit about that if someone doesn't know much about the critical rate at the wellhead.
Yeah, so you just you're basically tubing size, tubing pressure, and you can calculate. And there's graphs out there for operators, and there's lots of companies. Almost all the plunger lift companies will have a little graph that'll show you what your critical rate is at a certain pressure with a certain size tubing. So it kind of gives you an idea what your critical rate is. And basically, critical rate is the velocity or the gas velocity that you require to lift the heaviest fluid that's in that what is being produced.
Right.
And it is different between water and condensates and stuff like that. Like you can lift condensate many times where you won't move water very effectively. So it's a heavy critical rate for the heaviest fluid. I'm assuming that that's kind of the very quick description of it. But if you don't, and you don't have to know critical rate for the operators out there, but if they don't have one of those graphs, reach out to their plunger lift suppliers, or maybe they can respond to either you or me, and I'm sure we can get them one of those sheets that give them a kind of a basic understanding. And then if they're below that set point, hey, you should be looking at a conventional. Yeah. And the other thing that now you're saying, when do I run a conventional plunger? Now here's in vertical, like I said, it's pretty straightforward. You can use all the rule of thumbs and stuff like that. But when we start talking about horizontal now, create all sorts of interesting things, because beyond understanding what plunger is going to do the best is what actually moves the fluid the best in the horizontal. Mm-hmm. Because I've seen a lot of wells where we'll actually start out a very strong well running a conventional plunger. And the reason is we're only cycling it once or twice a day. Mm-hmm. We shut it in for that hour or whatever. We build up some energy, and that well kicks that plunger out. We clean a little bit of paraffin that's built up. And then that well has enough built up energy that it just cleans that horizontal section and lifts fluid like crazy for 12 hours or 24 hours or whatever. And then you can cycle it again, and it works really well in that application. And then as the well starts to lose that drive, then we'll start moving towards maybe a two-piece or maybe a free cycle. And then we'll actually, because now we need the plunger to do more of the work. So, initially the well is doing 100% of the work or 99.9% of the work. You're just using that plunger to a bit of a mechanical interface to move some paraffin out of the way and help maintain the tubing condition. And also ensuring that when you do shut that well and you bring it on, you're getting a really good sweep of that tubing, getting all the fluid out of the way so you can create the best differential between end of tubing and that formation, which can really let that well push fluid, and you'll get a lot of that water that's dropping out and all that stuff, and it'll move and the well will go again. But it's kind of like most guys, if you ask them, hey, what happens when you shut your well in for a couple hours and you just bring it back on? What does the well do?
Yeah.
Right? So if you automate that, you put a plunger in there to ensure that you're really getting that into tubing as low as possible, you're going to get a positive net result, even when the well is well above critical rate, because critical rate when we're talking about tubing, and that's a problem, another whole conversation. But in the tubing, when we're talking about critical rate, it's much, much lower number than it is when from end of tubing around that transition to the horizontal. I mean, you need 3, 4, or 5 times more fluid or gas velocity to move that fluid around that transitional area. So shutting these wells in and using that conventional can make a big difference on how that fluid moves. It's not dropping liquid water. It's not building in that transitional. So we start out with a conventional, possibly.
Well, I think I want to hit that real quick because that's so different than the vertical rules. The vertical rules say you go in order. You start at ball and sleeve, you move to free cycle, then you move over to conventional, and it is a transition, right? But what we're talking about here is, it's not by order. You end up getting conventional. You can start your well on a conventional if kind of what you were saying right there, like you're suggesting, is sometimes a well needs a clean sweep of the entire horizontal. Like you were mentioning, fluid flow and liquid buildup in the horizontal is challenging with plunger lift, and we have another podcast where we need to talk about that. But the 1 hour buildup, why would you put a ball and sleeve when you're doing a 1 hour buildup? It's a conventional plunger, right? So that's really, I think, kind of groundbreaking to hear, is that you don't always have to start with a ball and sleeve. It could be the conventional, right?
I mean, this is a truth that I have seen across all these horizontal wells. Production time, your total on per day, does not equate total production.
Right. Yes.
In a vertical well, it is much different. I mean, hours on equals production, but in a horizontal well, I don't see that. In fact, had a great conversation with some guys down in Midland, and they after a training, and they went out and tried some stuff, and they did that where I taught, don't worry about your time on, worry about what you need. Shut that well in, build up some energy, make some fluid move. Because if the well is flowing in a horizontal well, if you're flowing that well and it's not lifting liquid with the gas, that's liquid you're never going to get out of that well. Right? You have to use that gas, that energy, to drive that liquid out constantly.
That is so critical what you just said right there. Like, why are we producing the gas if it's not being used to get the liquid up, right? If gas is $50, I mean, maybe trending there, but it's not. The commodity is the oil, and also it's about deliquifying the well and making sure that we don't have that weight bearing down on the formation. So I think what you said right there around it's using the gas to get the liquid, and there's a better way to do it, and that could be by building up longer instead of the conventional thought of I want 10 minutes off, right?
We've seen this lots where we'll go out, pull a 2-piece plunger out with, and the well is more than, it'll sit there and run a 2-piece plunger, no off, exactly.
Yeah, absolutely.
No problem. We'll go out there and you can just, the well's running nice, everything's going good, and we'll switch out and we'll go to a free cycle, for example, and we'll give that thing 10 minutes off and, say 15 minutes after flow. And basically you shut the well in, plunger goes down, you bring it back on, it takes it 10 minutes to come up, it flows for 15 minutes. And all of a sudden you go from basically, 23 hours a day of on time down to 16. And then, but when you look at the total production, it actually is better.
It's a 30% cut, and you get more production.
And we get more production, and we see this all the time. And I say this to people, and they think I got horns growing out of my head. And it doesn't happen every time. But in these horizontal wells, you have to be willing to experiment with this and try it, because coming back to gas conservation, even the only tool we have to move fluid through that horizontal today that's really effective is the well's own energy. When that's gone, when it's used up, nothing's pushing that fluid down there. We're not reaching down. We're not putting pumps down there, at least effectively that I know of yet, that are really doing a good job, that aren't costing everybody a fortune. So you need to keep that fluid moving. If you keep that fluid moving, 2 miles of 4.5-inch horizontal holds an awful lot of fluid. It's a pretty big separator. And if I'm producing 100 barrels a day, I probably got 24 to 30 hours of retention time as that fluid's moving through that horizontal. So if I got water and oil and gas, what's my water doing? It's separating out. It's staying behind. It's not moving, because that gas going across the top is moving that fluid, the light ends to the tubing, but you're just changing the the percentage of water and oil. And eventually what's going to happen is you're going to get this big slug of water. And I think if you talk to anybody that's gone out, swabbed a well that's gone down on them, those horizontal wells, and if they produce water, which pretty well all of them do some percentage, and you ask them, well, what did you produce the first swab? And I'll bet you they'll say 99% water. And it's an 8% water cut. Well, what did the second swab do? Well, probably did 99% water, right? Because all that water is built up and got left behind. And that creates also, and that's again, this whole conversation about fluid movement in the horizontal. But by shutting that well in with that conventional plunger or shutting that well in, you can keep that fluid moving because you're using the energy to basically, control slug. It's forcing the well to slug that fluid and keep it moving to the tubing to where we can handle it.
I like that. Yeah. It's like you're letting it build up long enough to control the slug that's coming from the horizontal. Yeah. You're not letting the cycles dictate whether you get 80% oil or 10%. You're kind of the controller there. So I like that. And I think it's just really interesting, just the use of conventional early on in life. When you think of conventional and you think, well, these are conventional plungers, they must be really old. Or a conventional plunger well must be really old. It may not be. So very, very solid point there. And I think the piece, okay, so let's say it's not part of the early life of the well. It's actually, we're 3 years in, 2 years in, and I'm trying to figure out, I need to go from, I've got a Venturi style or some sort of free cycle plunger, and my well's starting to become, unreliable. How do I select? And when I say unreliable, it's you're missing runs now. You're having short cycles. There's some issues there. What do I do to figure out the next plunger to move to in the life cycle of an aging and pressure declining well?
Again, it kind of comes down to the buildup a little bit, right? So if I'm running a free cycle, my well, so let's say the well is whatever, 10,000 feet deep, or let's say it takes you 1 hour to get that plunger to the bottom. Okay, that's based on your rule of thumb numbers or your tracking, and that's a conventional plunger. If my well is ready to come on in 37 minutes because it's built up and it can lift that plunger, do we want to leave it shut in any longer than that? The answer is probably no. Yeah. So that means that really a conventional plunger is hurting you at that point, and you would continue to run a free cycle plunger because it can beat a bottom. Maybe it can beat a bottom in 20 minutes. That's why you don't need a great big bypass area. It can fall slow and and all that and still get down there. It gets down there in half the time, it's ready to come on in 30 minutes. Well, at 37, you can turn it on. But if I shut that well in and I'm not ready to lift until 57 minutes, I would run a regular conventional plunger because there's very little lost production through that. So it's again, it's kind of using the wells to tell you, and it's based on, well, how long does it take my plunger to get down there? How much time am I losing, right? If I'm ready to come on at 37 minutes, I'm missing 23 minutes of potential production time, which is going to reduce the number of cycles I can do per day, which is going to result in lost production, more than likely. And that's the thing. If you look at when I was talking about, shutting a well in longer and we get more off time, when you talk about that conventional plunger, we're saying, well, we're going to shut it 1 hour a day. It's still flowing 23 hours a day. If I talk about a free cycle where I'm shutting it in, say for 10 minutes and 15, and you can say, oh, geez, I'm only flowing 16 hours a day. But if you look at the way the well builds up, and is it still building up? Is it still bringing pressure in? Is the well still producing, basically? And if I get to the point where the well stops inflowing and becomes stagnant or fairly stagnant, and it's off for 15 minutes, then I'm losing. But if I'm shut in for 15 minutes and that well's still building up, and I can get that plunger to come on because it hits that magic, weight or energy rate, and I can bring it on, then great, because I'm just going to get all that energy that I brought into the horizontal. I'm going to go to a gigantic storage area. It's all going to come up and it's going to carry things through, and it's going to lift the fluid and push it through. And it's really using the well to tell you when it's time to switch.
But then what if I tweak shit? So that's what you find with a lot of the operators and optimizers is like, I like what it's doing, but like, what if I give it 2 extra minutes of afterflow time? The consequences of that is you don't build as efficiently, right? Because you're letting the formation kind of breathe too much, right? So that what I've seen with some of the operators is they'll keep off time the same. Let's just say it's 30 minutes, and then they'll start tweaking and raising their afterflow time, or even dropping it. But typically they're looking for a little bit more, so they go on the higher side. And then they're sitting there with a well that was before it was ready in 15 minutes. Now after a week, it's ready in 25 minutes, and now you have non-arrivals because it's not building up as long. Talking about that because then we have people doing set point changes, and some of those aren't helping the reliability of the well. So should we be tweaking afterflow time as much as people are?
Yeah, I think because you said it, every well's a snowflake. So there's no hard and fast rule on what's right or what's wrong with these wells, especially horizontal. I mean, but vertical, yeah. I mean, it's easy to again, they're very pretty much simple.
Absolutely.
But then when we're talking about a horizontal, you should try something. But the real key is making sure that you record it and you come back to it. And the biggest mistake I see guys make is they go out there and they got 50 wells to look after and they mess with 30 wells because they think they can get a few more. Well, then how do they track anything? Do they write it down? Do they come back? Do they analyze the data? And I mean, in what you guys are doing, that data analyzing that data, what's coming in is really going to give you that information. So you try it. Okay, well, I want to try adding 5 minutes to my flow time. And I record, well, what is my gas doing? What is my casing and tubing pressure doing? What is my liquid doing? And we should be also recording, what is my water doing? Because the very first thing you'll start seeing is water percentages will start to drop if the wells liquid loading. Unfortunately, most people don't have really good water recording methods, right? So you don't always see that, but where you got really good meters and when recording, you can see it very quickly when water percentage starts to change. Something's coming. The well's going to load up and die, or you're going to have that issue. And even if it was well above critical, but yeah, I would never tell anybody not to try. But what I would say is, if you're going to do it, you need to record it. You need to understand what it's going to do. Then when you get it to that point where it's stable, go the other way and do the same thing. Did it make it better? Did it make it worse? Like compare the two, and see, because again, is the problem that we're not flowing in the well long enough to bring in enough liquid, or is the problem we're not building enough energy to move the liquid to where the plunger can lift it? And they're two different problems, right? Totally. If we're shutting in the well, we're not flowing it long enough, and the well just doesn't have any liquid, and it's not and we just the GLRs are low enough, or or high enough that we just need to flow longer to get a liquid lift that's sure, then that was the right move. But if the problem was that really we're just losing the energy and the liquid's not moving, then that was the wrong move.
Yes.
And you need to actually reduce your afterflow time, or you reduce your afterflow, and then you maybe look at increase your close time or your build-up time. And that's it's one of the key things is when guys do stuff, don't change 3 different settings. Change one setting, wait for, I would suggest at least 48 hours till everything's stabilized, record the results, positive, negative, everything, make another change. And that's the only way you'll ever figure out these horizontal wells. And you can have 10 wells on a pad and end up with 10 different results from doing the same thing.
Wow. Yeah, I believe that.
Yeah, and as the guys do this, and if they start really recording that information, it becomes easier. It's really hard in the beginning because you're recording stuff, you're doing this, you do this, and it becomes labors. But once you'll start recognizing things, the patterns. We get back to those patterns again. You'll say, "Oh man, I've seen this before, and I know what that pattern means. What I've seen it. I see it in the flow rate. I see it in the casing or the tubing or whatever." And once they recognize those patterns, and they become more and more reactive to it, and it becomes easier and easier to have success.
So yeah, that's a big one right there. Is if we are working on the right plunger and we have the right off time, and we're tweaking things. The tweaking needs to be captured. So if it is captured, we can learn from it. And by learning from it, you can obviously operate the well in a more reliable fashion. So that's a big insight there is capturing it. I don't know if many people are doing that outside of Cigna right now and being able to measure the performance of it. So big opportunity there to have something automated for it. So that's really good, Clint. Yeah, so I think we talked pretty in depth about the different types of plungers. You said the three big ones are your ball and sleeves, your pacemakers, and then you have your second category, your free cycle, and thirdly your conventional. And you gave some good rules of thumb. But really, I think what you shared a lot of insight with me on is, we need to read these wells like their personalities, their build characteristics, and it is not a hard and fast rule of now that your well is 6 months old, or now that your well reaches X percentage of efficiency. Well, now let's swap it over to this type. It really is about being able to read and understand that its build characteristics. So that was really insightful for me, Clint, and just want to leave it to you to throw anything else at the audience. I will say we've got to talk about horizontals, and we've got to talk about liquid and horizontals and the way that fluid flows, because that's what we're dealing. The Packer thing, I think, is so insightful. So I think we've obviously have another conversation coming. But anything else to just share with plunger types to the audience?
Well, I guess let's talk about the what I call a seal type, when there's a pad or a brush or a solid,
Mm-hmm.
and making sure that you're using the right thing. And I know a lot of people have a tendency to move right to pad plungers, because of the efficiency, but in these, especially these horizontal wells, it's really important to make sure you consider the environment. I mean, sands and waxes and different things like that. So you want to be very careful on what you're running in them. And probably, 8 years ago, 10 years ago, when I was doing this, a pad plunger was the workhorse of plunger lift industry.
It was, yeah.
And today, it's solid conventional plungers, because we're doing so
Mm-hmm.
much in these shale wells, and there's so much paraffin and wax and
Mm-hmm.
other issues that you just can't have any of these extra moving parts in there that are really going to create a lot of issues.
Right.
So, and that's where we start making up inefficiencies by using longer solid plungers and things like that. So I guess that would be one thing. Really think about what you're going to put in there. And the last thing I would say is nobody should say to their operations, "Hey, don't touch it." What they should be saying is, touch it, record it, evaluate it, and let's figure out what makes more sense. Because you should never take away, there's nothing like standing beside the wellhead and hearing that plunger come in and seeing it.
Mm-hmm.
I mean, you can get the data that you get from your SCADA and stuff is critically important, but standing there and listening to it adds just a little bit more that you just don't get from that data itself, and it can be very insightful. And nobody runs something better than somebody that understands it, right? And and can make suggestions. So I don't think anybody should be scared. I think they need to be trained. I think they need to be safe. Safety is critical. But I'm a big supporter of making sure that anybody that's running a well and running a plunger lift has the opportunity to adjust it, learn from it, and understand it, so they become a much stronger part of the team.
That's great.
So,
yeah. Such a good conversation today, Clint. Really appreciate the time and the insight you shared with everyone. So thanks for knowledge dumping on us. And a quick plug for Clint Mason, just the Kaizen Well Solutions is doing some really great stuff around gas lift and plunger lift, and would really recommend just going to their website, checking them out. If they're in your local area, great people to use. If they don't happen to be in your basin yet, Clint's a great person to reach out to and just talk plunger lift. And there's other ways to help from afar. So would recommend talking with Kaizen, and just appreciate the time today, Clint.
You bet. Thanks, Spencer. And I enjoyed the conversation as well. I always do when we talk. It's always
yeah, man.
Interesting.
We can go for hours, can't we?
I know we could tell stories all day and bore everybody to death, but I enjoy it, so I really appreciate it.
All right, Clint. Thank you so much.
All right. Have a great New Year's.
Yeah, see you, buddy.